Hello everyone and welcome to the coronavirus edition of the 7th lecture from our signal theory class. In this lecture I will give you some additional information to the topics of the previous lecture and then we will move on to non-homogeneous systems. So first let's pick up at where the previous lecture ended and let's talk a little bit more about damping. I will try to demonstrate this on an example of a car. We have a car as before, except now the situation is complicated by the fact that there is a bump on the road. What is going to happen when the car hits the bump? Well, if the wheel axis was firmly fixed to the rest of the car, the entire car would jump. That is definitely not desirable, therefore we use wheel suspension, where the wheel can move up and down with respect to the rest of the car, and the wheel axis is not firmly fixed to the rest of the car, but it is held in position by a spring that can compress and extend. So when this wheel hits a bump, this spring compresses and only the wheel goes up, not the entire car. But the wheel suspension is not going to work well if you only use a spring to position your wheel. Why not? Well, to explain this, I will start with the worst case scenario, and that would be the case when you have an ideal spring with no friction or energy loss in the system. If some bump compresses such a spring in an ideal frictionless case, such a spring would start to oscillate and the wheel would start to jump up and down and it would never stop doing it. This response we call undamped. Of course, in the real world, this is not going to happen because there is always some friction or some kind of energy dissipation in the system. But still, even when you account for real-world friction or other energy dissipation, once the spring is compressed by some bump on the road, the wheel is going to start jumping up and down, even though now the oscillations are going to dissipate due to the friction or some other energy loss. You get what we call underdamped response. This movement is still undesirable because it is going to create considerable vibrations in your car. If you have trouble imagining this, let me show you what it looks like on a real car. This is a footage from a test where the car on the left manifests this kind of behavior, the underdamped oscillations. Of course, the real car is a bit more complex than a primitive second-order system, but qualitatively, the main idea is clearly visible. You can see that after hitting the bump, the wheel starts to jump up and down, and it takes some time for these oscillations to dissipate. And that is obviously not something that we want. What you would like to have is what you can see on the right-hand side of this video. After the wheel hits the bump, it returns to its previous position without oscillating, without jumping up and down, and without creating unnecessary vibration. So how do you achieve this behavior? Well, from the examples I have done on the last lecture and on the last exercise, you could see that I can move from this type of behavior to this type of behavior by adding some friction or some kind of energy dissipation into the system. And that is why in the car suspension we do not only use a spring to suspend a wheel, but we also use a damper. The damper is the thingy you can see inside of the spring. It is essentially a cylinder with a piston that resists motion. The addition of the damper into the system is equivalent to the addition of some friction or energy dissipation. So when you add a damper into your car suspension, the energy of the compressed spring will dissipate into the damper and the wheel will not start jump up and down. Instead, it will just return to the original position in a slower manner. Thus, you can turn your underdamped response to an overdamped or critically damped response. Now, what is the difference between the overdamped and critically damped response? Well, if your damper resists the motion too much, it will prevent compressing the spring, so if your wheel hits a bump, the spring will not compress sufficiently and your entire car will jump. Your spring will compress only a little, and then it will return to the original position very slowly. This is what we call the overdamped response. We provided more damping than we had to prevent oscillations. So what is the minimal amount of damping we need to provide to suppress oscillations? Well, that is the critical damping when the system has the critically damped response. With this damping, the damper allows your wheel to move the most without creating oscillations. So when you design a system, be that a wheel suspension or inverse pendulum or an autopilot in a plane, you probably want to achieve a response close to this one. The last time I showed you that you can quickly see what type of response you get from the position of the roots of your characteristic equation. Two roots on the imaginary axis correspond to the undamped system. Two complex roots in the left-hand side of the complex plane correspond to the underdamped system. One double root on the left-hand side of the complex plane corresponds to the critically damped system, and two real roots on the left-hand side of the complex plane correspond to the overdamped system. In addition to the roots of the characteristic equation, there is another way how to read the type of damping in your system directly from the coefficients of your differential equation. For this, we use so-called damping ratio, and in addition to the damping ratio, we also use so-called natural frequency. This is how it works. You take your second-order differential equation with constant coefficients. You divide the equation with the coefficient a2 so that you get non-unity constants only in front of the first derivative and in front of the zero derivative. Now you denote this constant as omega naught squared, and you denote this constant as 2 times zeta times omega naught. Consequently, this is your characteristic equation. Students sometimes have problems imagining this, so this is a specific example. This is your differential equation. First, you divide by the coefficient with the highest derivative and you get this. Then, this is your omega naught squared, which means that your omega naught is 3. And this is your 2 times zeta times omega naught, which means that your zeta is 1. Now, when you have your differential equation in this form and you know what the zeta and omega naught are, you can start searching for the roots of the characteristic equation. The discriminant of the characteristic equation is this, and you can rewrite it like this. The roots of the characteristic equation can now be written like this, and this expression can be simplified into this one. Now, when you take a look at these roots of the characteristic equation, you can see that depending on zeta, you will get different types of the roots. For zeta greater than 1, zeta squared minus 1 will be positive. This square root will be real, and you will get 2 real roots of the characteristic equation. If zeta is greater than 1, you get 2 real roots of the characteristic equation. Your general solution consists of 2 real exponentials, and you get an overdamped case. If your zeta is less than 1 but positive, zeta squared minus 1 will be negative. This square root will be imaginary, and you will end up with 2 complex conjugate roots. Note that the real part of the roots will be negative, so your system will be stable. So, if your zeta is less than 1 but positive, you will get 2 complex conjugate roots. Your general solution will consist of 2 complex exponentials, or equivalently of exponentially damped sum of sine and cosine, and you get the underdamped case. Now, if your zeta is 0, the real part of your roots will be 0, and you will get purely imaginary roots that will be equal to plus minus omega naught times j. If your zeta is 0, your roots will be plus minus j omega naught. In this case, your general solution is given by the sum of cosine and sine, and you have the underdamped case. If your zeta is 1, then this expression is 0, and you get a single double root equal to minus zeta times omega naught. If your zeta is 1, then you get a single double root minus zeta times omega naught. In this case, your general solution should look like this, and this is the critically damped case. Last, if your omega was negative, you would get an unstable system because the real part of your roots would be positive. But this approach is mostly intended for stable systems in which these coefficients will be positive and consequently omega naught will be real. For unstable systems, we do not use this, and if a system is unstable, we do not judge its damping. But for those stable systems out there, there is this zeta, the value of which will tell you what kind of damping the system has, and you can compute zeta directly from the coefficients of the differential equation. This zeta actually has a name, and it is called the damping ratio. In addition to zeta, this omega naught also has a name, and it is called the natural frequency or the frequency of undamped oscillations. Why? Well, because if we have the case with undamped oscillations, which is this case, the omega naught will be the frequency with which the system will oscillate. Okay, that is all about damping. Now let's move on to non-homogeneous systems. In the last lecture we had homogeneous systems which had differential equations with zero right-hand side. You can imagine homogeneous systems as systems that do not have any inputs or systems that have zero at their inputs. A non-homogeneous system is a system that has a non-zero input. When you describe it with a differential equation, the input signal and sometimes even its derivatives will appear in that differential equation, and we typically write them on the right-hand side, which will now not be zero. Obviously, we will be primarily interested in non-homogeneous systems that have some non-zero inputs, so we need to learn how to solve this kind of differential equation. That means that we need to find what is the output of this system when we know its input. The solution is typically found in two steps. In the first step, you will find one particular solution that will fit this differential equation, and you do not care what the initial conditions of this solution are. They can be anything. In the second step, you will adjust the solution from the first step so that it fits some given initial conditions. We will start with that first step. That is, we will try to find one particular solution that fits our differential equation, or in other words, we will try to find any one way how our system can behave. Not to work on purely theoretical level, I will demonstrate the individual techniques on this system. It is an RC circuit with the input voltage V1 and the output voltage V2. If you describe this circuit using circuit equations, you will get this differential equation. And you can see that when I put the terms with the output voltage on the left hand side, on the right hand side, I'm left with the input voltage. So this is not homogeneous. Now, if we want to find one particular solution of this circuit, we need to find one form of voltage V2 that we can observe at the output of our system. How can we do that? Well, sometimes you can use the simplest of the approaches and just guess the particular solution from the nature of your system. For example, if my input voltage is a constant uppercase V1, what could I observe in this case at the output of this circuit? Well, if you have some experience with electrical circuits, you will quickly see that one possibility is that this capacitor will be charged to that constant input voltage, and the output voltage will be the same constant voltage as is the input voltage. If the input and output voltage are the same, no current will flow through this resistor, and the circuit can stay like this indefinitely. So this is one way how this circuit can behave, and this we can use as our particular solution. This subscript P denotes that this is our particular solution. But what if your input signal or your system are too complicated to guess the particular solution like this? Or what if you simply cannot figure out even this simple case? Well, in that case, you can use some prepared prototypes in which you just need to compute the values of some constants. Specifically, if your input signal happens to be in the form of a polynomial of order n, then you can find a particular solution also in the form of a polynomial of order n. All you need to do is to figure out these constants c0, c1 and so on. Let's take this circuit as an example, and let's say that my input, that is the input voltage, is still a constant uppercase V1. This is a zero-order polynomial, so I can look for the solution in the form of a zero-order polynomial C0. How can I find what the C0 is? Well, I will just substitute this prototype of my particular solution into my differential equation, and I will find what C0 needs to be for equation to hold. So this is my differential equation, and now I will substitute my particular solution, that is this constant C0, for V2. Also, I will substitute my input signal V1, and this is what I get. Here, the derivative of this constant is 0, so from this I can see that my C0 needs to be V1. Thus, my particular solution is this uppercase V1. This is the same result as I got over here. So this is my particular solution. It is a solution that fits my differential equation, but if I had some given initial conditions, it does not have to fit them yet. Now let's take a look at a different and substantially more useful form of an input signal. Let's say we would like to know what is the output of a system if the input is a pure tone, if the input is, for example, a cosine. Well, a cosine may be a bit difficult to tackle directly, so let's break it down a little bit. From lecture 1, we know that this cosine can be written as two exponentials, one at frequency omega naught and one at frequency minus omega naught. Now, instead of doing the entire cosine, I will start with this first exponential, which is actually quite easy. It is actually quite useful to understand what I'm doing here in the spectral domain. The spectrum of the cosine would be two Dirac delta pulses, one at positive frequency omega naught and one at negative frequency omega naught. Each of those Dirac delta pulses correspond to one of these exponentials. If for my input signal I will take only this first exponential, in the spectral domain I will have only one Dirac delta pulse at frequency omega naught. If you want to verify that this is the spectrum of this exponential, just compute the inverse Fourier transform of this spectrum, and if you scale everything properly, you get this exponential. But the most important thing to note here is that now we are feeding the system with a signal that is at a single frequency. So essentially we will now examine what the system will do with this single frequency omega naught. Turns out that if the input of your system is this exponential, the output, that is one particular solution, will be the same exponential except multiplied by some complex number. Of course, in the case of this circuit, it is purely theoretical because we cannot feed this circuit a complex voltage. But we can consider this case on a purely mathematical and theoretical level, and when we do, it will actually reward us with some useful and practical results. So first, let's take a look how we can find this complex constant h, and after we will examine why, if we feed the system this complex exponential, the system only multiplies it with a constant. First, to find this h, we will take this input signal and this output signal, and we will substitute them into our differential equation. Here you have it substituted. Now I take the derivative, which will give me this, and here I can cancel out the exponentials, which will give me this, and from there I get this. This will be the complex number that will multiply this exponential at the output. And one more thing, this is just a complex number, but you can see that for different frequencies omega naught, I get different complex numbers. Therefore, this is actually a function of omega naught, so I can denote it as h of omega naught. So, I can write that the output of this circuit will be this complex exponential. And this complex exponential will be the same complex exponential that was at the input of the system, but multiplied by this complex number that for different frequencies omega naught I have denoted as h of omega naught. Here I have drawn it graphically. If I feed the system a complex exponential like this one, I will get the same exponential, but it will be multiplied by this complex number. Now this complex number can be written using its magnitude and phase like this. Here you can combine these two exponentials and you get this. And here you can see that the magnitude of h will tell you how your exponential is amplified, and the phase of h will tell you how it is phase shifted. So this function h as a whole will tell you how your input will be changed in magnitude and in phase at frequency omega naught. We already worked with this kind of function, and we called it the frequency characteristic. The frequency characteristic will tell you how at some frequency your signal is amplified and phase shifted by your system. So here we have found the frequency characteristic in a time continuous system. And now that we know the frequency characteristic of our system, that is this circuit, we can find what type of filter it is. When I take the magnitude of this frequency characteristic, which is this, and I plot it, I get this, and I can see that my circuit is actually a low-pass filter. Okay, now that we know how a system is transferring a single frequency, we could go back and examine how a system will transfer a cosine that is actually composed of two frequencies. But before I do that, I will show you some extra maths where I will demonstrate this concept in a more general manner. In this case, I have a general second-order differential equation, and here I will assume that my input is a completely general complex exponential. That is an exponential with some complex amplitude and some complex frequency. Now, in this case, it turns out that my output will be the same complex exponential multiplied by some complex number h. In these following lines, I'm showing why this is true. To prove that this input really creates this output, I need to put these complex exponentials into my differential equation and see if it holds. So here I have substituted this complex exponential for the input x and this complex exponential for the output y. The rest is similar to the previous example. I take derivatives, I cancel out the exponentials and a's, and I'm left with this. From here I can find that the complex number h is this. And here you can see that h is actually dependent on s, so I can denote this as h of s. So if I set the h to this, my differential equation will hold, and this will be the output for this input. And this will work always unless I'm really unlucky and for this complex frequency, this s, this denominator is 0. But when it is not, if this is the input, this will be my output. So in general, if we feed our system a complex exponential, we will get the same complex exponential, which will just be multiplied by a complex number. This actually means that for a system described by an ordinary differential equation with constant coefficients, the complex exponential is a special function. If you fed this system with any other function, you will not get the same function just multiplied by a complex number. If you fed this system a sine, in general at the output you would not only get a multiple of a sine. If you fed this system a unit step, at the output you would not only get the unit step multiplied by a number. If you fed this system a Dirac delta pulse, the output would be an impulse response that is not just a Dirac delta pulse multiplied by a number. But if you feed the system a complex exponential, the only thing that the system does to this complex exponential is that it multiplies it with a complex number. Well, this result gets mathematicians excited, and they even gave this function a name. They call it an eigenfunction. So an eigenfunction of a system is a function which you can put at the input of a system, and the system will only multiply it by a constant. For the systems described by an ordinary differential equation with constant coefficients, the eigenfunction is the complex exponential. Other systems can have different eigenfunctions. Anyway, this slide was mostly a side trip to theory that you do not need right now, even though you would do well to remember it for later. Now let's get back and let's take a look at how we can figure out what will be the output of our system when the input is a cosine and maybe even a more complicated function. Well, if we wanted to do a cosine, we already know what the system does with a single exponential. But we still need to find out what our system does with a combination of two signals. That I will examine in this slide. Here I will take a look at what happens when I feed my system this combination of input signals. This is so-called linear combination, which means that I multiply my signals with constants and add them together. Now, if my system gives me output y1 for input x1 and my system gives me output y2 for input x2, then for this linear combination of x1 and x2, my system will give me the same linear combination of y1 and y2. How can I check if this is true? Here it is. If the input x1 creates the output y1, then mathematically y1 and x1 must fit the differential equation of the system. In general, on the right hand side you can have derivatives of x1 as well, but to save you some ugly math, I'm just doing this without any derivatives of x1. If you want, you can do this with derivatives of the input signal at home. But without the derivatives of the input signal, if the input signal x2 creates output y2, then signals x2 and y2 must also fit the differential equation of the system. Now, if I use this linear combination of x1 and x2 as my input, and I expect this linear combination of y1 and y2 to be my output, then these signals x and y must also satisfy my differential equation. So let's check that. Here is my differential equation with signals x and y, and here I substituted the linear combination for x and y. I can rearrange this differential equation into this form, where I have put together all the terms with y1 and all the terms with y2. Now, when I use this differential equation, I can see that this is supposed to be equal to x1. And when I use this differential equation, I can see that this is supposed to be equal to x2. And you can see that left hand side is equal to the right hand side, and indeed this differential equation holds, and this is the output for this input. Additionally, if you recall the definition of linearity, you will see that our system, described by the ordinary differential equation with constant coefficients, seems to fulfill the definition of linearity. Therefore, we could say that it is linear. But later I will show you that this linearity can still be messed up by the initial conditions. So at this point, I will just say that the system can be linear, but I will examine its linearity later. In a circuit like this, the linearity often goes under the name the principle of superposition. That is, if you know that for input V11 you get the output V21, and you know that for input V12 you get output V22, then the combination of the inputs V11 and V12 will give you the output given as the combination of V21 and V22. Now that we know how a linear combination is being transferred through a system, we can finally figure out how our system is going to respond to a pure tone in the form of a cosine function. So, if to the input of my system I feed a cosine, that is, if the input voltage of my circuit is a cosine, then I can find the output of my system in the following manner. First, I will write the cosine as a linear combination of two exponentials. What my system does with these exponentials separately, we have already figured out. When this exponential is passed through the system, it will be multiplied by a complex number that corresponds to the system's frequency characteristic at frequency omega. When this exponential is passed through the system, it will be multiplied by a complex number that corresponds to the system's frequency characteristic at frequency minus omega. Now, what will system do with a linear combination of these two exponentials? The output will be the same linear combination of these two complex exponentials. This will be my output. Here, this complex exponential will get multiplied by this a over 2, and here this complex exponential is multiplied by this a over 2. Here you should note again that this is my frequency characteristic, which I can write in this polar form using its magnitude and phase. And this is also my frequency characteristic, except at negative frequency. But here I can use the symmetry in the CT-FT spectrum, and I can write that the value of this frequency characteristic is complex conjugate of the frequency characteristic for the same positive frequency. This I can write in the polar form like this. Now I can combine these two exponentials and these two exponentials, and I will get this, which when you examine is nothing else but a cosine except scaled in amplitude and shifted in phase. And of course the amplitude frequency characteristic tells us how the cosine is amplified in amplitude, and the phase frequency characteristic tells us how the cosine is shifted in phase. If I substitute it for the frequency characteristic of this circuit, I would actually get this formula for the output voltage of my circuit. So this is how our system responds to a cosine. It changes its amplitude and shifts its phase. And the amplification in amplitude is given by the amplitude frequency characteristic, and the shift in phase is given by the phase frequency characteristic. When your input signal is a sine, the result is pretty much the same. The sine will be changed in amplitude and shifted in phase, and the amplification in amplitude is given by the amplitude frequency characteristic, and the shift in phase is given by the phase frequency characteristic. Okay, so we have figured out how our system responds to a sine and to a cosine because we were able to break them into complex exponentials, which are eigenfunctions of our system, and we know how those are being passed through a system. They are just being multiplied by a complex number. But what happens if the input of your system is a general signal and you cannot decompose it into complex exponentials as easily as the cosine or a sine? Well, in case of a general signal, the decomposition into complex exponentials may not be as easy as for the cosine or a sine, but you certainly know how to do it. If your input signal is periodic, then you know that you can write it as a Fourier series, which is nothing more than a linear combination of infinitely many complex exponentials, the complex amplitude of which are the coefficients of the Fourier series, which you know how to compute. So your general periodic signal you can express as a sum of complex exponentials, and you know how these individual complex exponentials are being transferred by the system. They are just multiplied by a complex number, which is the system's frequency characteristic at the corresponding frequency. So this Fourier series will be your output signal. It may not fit your initial conditions, but you can use it as a particular solution. Now, what if your signal is not periodic? No problem. An aperiodic signal we can express using the inverse Fourier transform like this. Now I do not have a sum here, now I have an integral, but the principle is pretty much the same. This signal is expressed as a combination of uncountably many complex exponentials, the complex amplitude of which are given by the spectrum of the input signal. When these exponentials are passed through the system multiplies each of them with a complex number that corresponds to the system's frequency characteristic at the frequency of the complex exponential. So this will become my output signal. It may not fit the initial conditions yet, but I can use it as a particular solution. So, when you are dealing with a continuous time system described by an ordinary differential equation with constant coefficients, this is how you can find the output signal for a given input signal using the knowledge about the eigenfunctions of the system and the Fourier series or the continuous Fourier transform. Okay, so on the previous slides, I have showed you several ways how you can find the output of your system if you know the input. But all these techniques will give you outputs that do not have to fit your initial conditions. So what do you have to do if you want to find the output of your system so that it will actually fit some initial conditions? Well, you need to do this. This is your non-homogeneous differential equation, and these are your initial conditions. To find a solution that fits these initial conditions, you first need to find that one particular solution that does not have to fit your initial conditions. How to do that I have shown you on those previous slides. As the next step, you need to add something to your particular solution. This something should not change the fact that this is a solution of your differential equation, but that something should allow you to adjust your particular solution for your initial conditions. But how do you find this something? Well, let's see what we can add to our particular solution so that the result is still a solution of my differential equation. To see this, I'll take my differential equation and I'll substitute this for y of t. This is what I get. Now I can distribute these derivatives and rearrange the individual terms so that I put together all the terms with the particular solution y sub p, and I put together all the terms with the new function y sub h. This function y sub p of t is the particular solution that already satisfies my differential equation. So when you note that this is the left-hand side of my differential equation, this must be equal to the right-hand side of my differential equation. Now, if I want this equation to hold, it is going to happen only if this is 0. So we need to find y sub h as the solution to this differential equation. And this is actually our original differential equation, except here we removed all the inputs to the system. We turned this non-homogeneous equation into a homogeneous one. In fact, this equation is called the associated homogeneous equation. And when you solve this associated homogeneous equation, how to do that we learned on the previous lecture, you get a solution like this. Sometimes this second exponential is multiplied by t. Lucky for us, the solution of the associated homogeneous equation has some constants that we used and still can use to fit our solution to the initial conditions. So, I can construct the general solution of my differential equation as the sum of one particular solution and the solution of the associated homogeneous equation. This y sub h contains a couple of constants that I can set to different values, which will give me different behaviors of my system. In fact, mathematicians know how to show that this combination can describe all the behaviors of my system. Therefore, we call it the general solution. Now, if my initial conditions are set, I can use them to compute those constants essentially in the same manner as we did in the case of the homogeneous differential equation on the previous lecture. So this is how you find the output of your non-homogeneous system if you are given an input and some initial conditions.